Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the multi-quadrant operation of DC drive fed from a converter. So, we have seen in the last lecture that by using mechanical switch, we can go from forward motoring to forward braking, then reverse motoring. That is what we are discussing in the last lecture. So, here we have the armature and we have the reversible switches here, and then the converter is feeding the armature of the DC machine. So, we can go from first quadrant, that is forward motoring, to forward braking by reversing the switch after the current comes down to 0. Then we can reverse the speed and we go to reverse motoring. Now, using this mechanical contactors is sometimes very cumbersome. This requires frequent maintenance, and also this is not a very smooth way of moving from one quadrant to the other quadrant. The other option is to have a dual converter. So, we will be discussing the concept of dual converter in today's lecture. So, there is a second method we will be using here, dual converter fed DC drive. Now, let us see how the topology looks like. So, we have two types of dual converter. One is called a circulating current type, circulating current type dual converter, and the other one is called non-circulating current type dual converter. For today's discussion, we will take up circulating current type dual converter and see how the connection is made with the armature circuit. So, we will take up the first one, that is the circulating current type. And in this case, we have the two converters. I am just showing in the form of a box, and this is a SCR bridge. It is a 3-phase bridge, let us say. It is a 3-phase full controlled bridge converter. So, we have two bridges, two converter bridges. Now, these two converter bridges are connected in anti-parallel, but not directly. They are connected through intergroup reactor. So, this is how the two converters are connected in parallel or in anti-parallel, and the armature is fed from the center tap of the converter. This so, we call this to be L 1, the inductor or reactor L 1, this is L 2, and these two converters are being supplied with a 3-phase supply. The 3-phase supply is coming from the mains, and the second phase is also connected to the converter, second converter. Here the input are all coming from the mains, the same input is connected here. So, we call it to be converter A, this is the converter B, and the voltage output of converter A is called V A, and the voltage output of converter B is called V B. Because it is antiparallel, we will put positive sign here and we will put the negative sign here. So, these two bridges are antiparallelly connected. The armature current direction is usually shown in this direction, that is I A, and the back EMF, the voltage here is V A, the armature voltage is V A. Now, this converter, these two converter will only carry current in one direction, because they are unidirectional switches. So, the current can only flow, this is the current flow from converter A and this is the current flow from converter B. So, and we have this intergroup reactor, these reactors are connected to limit the circulating current. So, the reactor L1 and L2, reactor L1 and L2 or inductor are used to limit the circulating current between the converter bridges. These are AC mains. Now, usually the voltage has to be same, V A and V B has to be same ideally, but since they are converters, although the average voltage can be made same, the instantaneous voltage will not be exactly same. So, there will be a circulating current between the two bridges that has to be minimized. So, this is the circulating current that can flow between the two bridges I C. So, if you want to minimize this circulating current I C, we have to use the intergroup or interbridge reactors L1 and L2. Now, let us see in how many quadrants can this operate. So, if we do the VI plot, the voltage and current plot, voltage in the y axis and current in the x axis, that plot will look like this. This is the voltage, we are talking about the armature voltage, that is V A, and armature current, that is I A. So, when we do these two plots, we plot V A and I A, this is the first quadrant, we have the second quadrant here, the third quadrant is here, and this is the fourth quadrant. For the first quadrant, V A is positive and I A is negative. So, the current this I A has to come from one of the bridges, either it has to come from bridge A or the converter A, or it has to come from converter B. Now, if the current is positive, it has to come from converter A. So, and if the current is negative, it has to come from converter B, because the converter B can supply only in this direction. This is the converter B current, and converter A can supply in this direction. So, we sometimes call converter A to be a positive converter, this can supply the positive current, and or P converter. Converter B sometimes is called a negative converter, or this can supply the negative current. So, in this case, the converter A here, converter A the voltage can be negative, but the current will always be positive. Converter A can operate in quadrant 1 and 4, quadrants 1 and 4, because for converter A the voltage can be negative, because this is a full control bridge. When we have alpha A is higher than 90, voltage can be made negative, but the current has to be positive. So, converter A will operate in the VI plane in quadrant 1 and quadrant 4, current remaining positive. We have the voltage which can be made negative. So, this is for converter A. So, converter A will operate in quadrant A 1 and quadrant 4. What about converter B? This is converter A. What about converter B? Converter B will operate for reversible voltage, but negative current. So, converter B will operate for negative current, it can supply only the negative current. So, converter B operates in quadrant 3 and quadrant 2. So, converter B here the voltage can be reversible, it operates in quadrants 3 and quadrant 2. So, we have 4 different quadrants. So, this is called a 4 quadrant converter. Since we can operate in all possible quadrants, so when we take a dual converter, we get a 4 quadrant converter. So, this combinedly called a 4 quadrant converter. Now, let us see what is the relationship between the triggering angle alpha. This is converter A, this operates at a triggering angle which is alpha A. Converter B operates at a triggering angle which is alpha B, and both the converters are operated at the same time. Converter A and converter B are simultaneously operated, they are applied with the triggering pulses and they have the output voltage. Now, what we have to be positive about this, that the two converters, the voltages have to be equal, because these inductors they do not have any resistance, inductor L1 and L2. We have to be sure that these two voltages have to be equal. So, what we do here, we write down the voltage equation, that VA is equal to minus VB, they have to be equal. It means the negative of this voltage VB should be equal to VA, or we can say that VA plus VB is equal to 0. So, these two converters voltage in this loop will add up to 0. The average voltage of converter A plus the average voltage of converter B should be equal to 0, because the inductors L1 and L2 they do not have any average drop. So, when we say that VA plus VB equal to 0, what is VA? It is a fully controlled bridge. So, we have 3 Vm by pi into cos alpha A plus 3 Vm by pi into cos alpha B is equal to 0, or cos alpha A plus cos alpha B is equal to 0, or if we simplify this further, we get a relationship alpha A plus alpha B is equal to 180 degree. So, it means the triggering angle of the two converter will sum up to 180 degree. If one is operating at a triggering angle 60 degree, the other should be operating at a triggering angle which is 180 minus 60 degree. So, we can find out one triggering angle when the other is known. So, this is the relationship here. Now, for forward motoring and braking, we have to make sure that the drive operates in all 4 quadrant. So, for forward motoring and forward braking, the back EMF is positive, E is positive. When you say forward, the speed is positive. So, it means the speed is higher than 0. Now, when the speed is 0, converter A will be operating in rectifying mode, will be rectifying, and converter B will be inverting. Now, what is the meaning of this? When we say converter A is rectifying, it means alpha A is from 0 to 90. When we say converter B will be inverting, it is basically operating at a negative output voltage, which means alpha B should be between 90 to 180. So, one thing is very important, that when we are talking about forward motoring and forward braking, the voltage V A is positive. This is positive voltage. So, V A is positive. So, which means the motor is in the forward condition. So, V A and V B will be positive. So, alpha A will be from 0 to 90 and alpha B from 90 to 180. Now, let us see if it is reverse motoring. If it is reverse motoring, we have to change the polarity of the supply voltage, because the back EMF has to be negative. So, if the back EMF is negative, the supply voltage has to be negative. So, for reverse motoring and reverse braking, for reverse motoring and reverse braking, what we have here? For reverse, the back EMF is negative, the speed is negative. When we say reverse, the speed has to be negative, which means the back EMF is also negative. So, this is the meaning of reverse. Now, if it is reverse motoring and reverse braking, what is the situation of converter 1? So, converter 1 or converter A, output voltage has to be negative. So, it means converter A will be in the inverting mode. So, it means alpha A has to be from 90 to 180. And what about converter B? Converter B will be rectifying, which means alpha B has to be between 0 to 90. So, when we say reverse motoring, the voltage is reversed. So, it means converter A will be inverting and converter B will be rectifying. So, this is the operation of circulating current type dual converter. Now, we have another type of dual converter called non-circulating current type dual converter. So, we will very briefly discuss about that. We have the second type of dual converter, non-circulating current type dual converter. Now, in this case, if we draw the circuit, we have again the two bridges here, and they are supplied from the the same 3-phase supply. The bridges are connected in antiparallel. Now, this is ABC is also the same as ABC, same supply. Now, they are directly connected. These two converters, converter A and converter B are directly connected, and the armature is connected from the common point, this is armature. Now, in this case converter A and converter B are not operated at the same time, they are operated only one at a time, either converter A or converter B. When we want it to be forward motoring and forward braking, we use converter A. When we want the drive to be in the reverse motoring and reverse braking, we use converter B. So, converter A is only responsible to supply the positive current, and converter B can only supply the negative current. So, for only one converter is operated at a time, only one converter is operated at a time. Okay. There is no circulating current, there is no circulating current. The output current has to be sensed. This is the output current I A, and we have the output voltage, that is V A. So, when we want the output current to be positive, we trigger converter A. When we want the output current to be negative, we trigger converter B. So, for I A to be positive, converter A is triggered. For I A to be negative, converter B has to be triggered. And when we change the triggering from A to B, there is a dead time between the two triggering to ensure that one bridge is completely off before the next bridge is triggered. Unless we do that, there will be short circuit of the AC supply. So, a dead time is maintained, a dead time is maintained between turning off of converter A and turning on of converter B and vice versa. So, when we change from the operation of converter A to converter B, since there is no intergroup reactor, we make sure that one converter is completely off before we trigger the next converter. So, we allow a dead time between the two converters. Now, this is about the non-circulating current dual converter. Now, we have another way of going for the multi-quadrant operation, that is the reversing the field current. We have the armature and field, we have seen the armature control, we can also reverse the back EMF by doing the field control. So, we will be discussing about the field control right now. So, the third way of operating in multi-quadrant is field current reversal. So, in this case the armature is supplied from bridge. As usual, we have fully controlled bridge here, maybe a 3-phase bridge in this case, and we supply the armature from this fully controlled bridge. The field is separately excited, but the field is fed from another set of bridges. So, we have two bridges. which are used to supply the field winding. We have something like dual converter type of configuration. We have two antiparallel bridges, and these two bridges feed the field winding. So, this is the field winding, and we have the 3-phase supply to the two bridges here. So, this bridge is called the field converter 1, this bridge is called field converter 2, and we have the field current which is IF, and the triggering angle of the first bridge is called alpha f 1, the triggering angle of the second bridge is called alpha f 2. And in the armature side, we supply the armature current IA, and we have the armature voltage, that is VA here, and the triggering angle of the armature bridge is alpha A here. Now, how we reverse the back EMF? The back EMF is reversed in the following fashion. Suppose we are operating under forward motoring. Now, when we are operating under forward motoring, what we do first? We advance the triggering angle alpha. So, this is the first operation. So, if you want to reverse the field, advance alpha A. So, when we advance alpha A, what happens? VA becomes negative. So, IA comes down to 0, IA becomes 0. So, when IA becomes 0 or the armature current becomes 0, there is no armature current here. So, we give a dead time. So, switch off armature converter. So, we switch off the armature converter and then give a dead time, allow a dead time of about 10 millisecond, and then what we do here, we advance alpha f 1, advance alpha f 1. Say for example, alpha f 1 was initially finite. So, the current is positive. So, when we advance alpha f 1, IF becomes negative, IF becomes 0. So, when IF becomes 0, we switch off field converter 1 and we allow a dead time of about 10 millisecond and start field converter 2, and when we start the field converter 2, the current reverses, the current starts flowing in this direction. Earlier the current was in this direction, current has now reversed. So, this is how we reverse the back EMF. So, the back EMF reverses. When the back EMF reverses, we start the armature converter. So, this is how we go from forward motoring, forward braking and reverse motoring. So, the torque is negative now because the field current has reversed. So, this is one of the ways of going from one quadrant to the other quadrant. So, we stop here for today's lecture. We will continue in the next class.